Welcome to Lecture 6 in Symmetry, Structure, and Tensor Properties and Materials. In this lecture, now that we've talked about our symbols and we've already given you one example of a combination of operations with a rotational axis and a translation vector, we're going to now develop some of the 2D nets, the most simple ones, which can be created by combining a translation vector with a rotation axis. And what we're going to find out, of course, is that we'll have a normal oblique, we'll have a square, and then we'll have hexagonal nets from the combinations that we're going to talk about in the following slides. Before we go into that, remember we arrived at how, from our simple theorem of combining any rotation with a translation vector in the most generic sense, that the fivefold axis can't fill space. Now, I just wanted to make sure that we all understand you can have fivefold symmetry. In fact, here's a very simple rendition of that, a starfish, which has fivefold symmetry. But remember, what we're doing when we combine with the translation vector is that it has to fill space. So I can have any kind of symmetry I want if I just go through a single point, which is what's happening here. And later, we're going to call these point groups, right? We can come up with all sorts of symmetries around a single point, right? But I haven't combined that yet with a translation vector. And so, you can have, in this case, a fivefold symmetry sitting on a single point. What you can't do is put in a periodic array of points that are spaced by translation vector t, right? So that's the important distinguishing feature. I want to make sure that when we talk about we can't have fivefold symmetry, we don't mean we can't have that symmetry. Clearly, I can draw a pentagon, I can draw a starfish, but it can only be about a point. I can't fill space with it. If you try to do it, by the way, just to prove to yourself by hand, you'll see that here I've just tiled a few pentagons together, and what you'll see is that you can't get it to work. Now, there's a famous thing called the Penrose tiling, where actually, if you fill this space, you'll notice that you're missing little. Well, this is one shape that you can do it with. You're missing little diamonds, and if you actually put these diamonds in, then you can fill space. And so if you have two kinds of symmetries, you can actually fill space with pentagons, but you need to have another symmetry in there. All right, so let's start off with the most simple one, the most straightforward one. And we can handle this pretty quickly. Here's our starting point for a translation vector. And we've already kind of done this one because we said, all right, I'm going to put a twofold axis, right? So basically, the way to think about it, I'm doing this geometric thing where I'm combining a translation vector and a twofold axis. So if I do that, we know what this means. I have to have a 180-degree operation here, right? It's going to end here, and if I drew it the same length, that's t in the other direction, minus t essentially, right? So what you realize is, well, of course, a twofold axis is completely consistent with, even in 1D, a linear array. So for sure, I can produce a twofold axis because it just creates the same parallel lines. Now, it doesn't mean I have to have a twofold axis, by the way. There's an important distinguishing feature. So I can have a oblique lattice that I talked about before in our simplest case. We're going to be calling this the oblique lattice. And remember, that's when we first introduced the standard cell. Remember, this is the standard cell for that kind of primitive lattice. And so this oblique is already in existence. We get that just by determining, remember, that T2 couldn't be parallel to T1, and you automatically get this. But it means that a twofold axis exists along any one of these things. So for example, you can see I have a twofold axis here, right? And if this is T2, I have a twofold axis here. So actually it doesn't introduce any newness about this thing. Like I said, later there's going to be other elements in combination with this twofold axis that change things. But right now, yes, you can add it, but it doesn't change anything about this oblique lattice. So our conclusion here is, of course, you can put in a twofold rotation, but it just creates parallel lines, so nothing new. And it shows the same example that we've already used, the oblique lattice. So let's go to the next one, which is, let's change color just for difference here. And let's add our threefold axis to, sorry, just a generic thing, right? And we kind of know what that looks like. Remember, we had the beginning of this lattice, because when we want to rotate through 120 degrees for a threefold axis, right? 360 divided by 3. I have no idea if this is exactly 120 degrees, but then you would have the same thing the other direction. If I can draw this somewhat symmetrically. And this is just in case you look at this later, make sure you know that that's supposed to be 120 degrees too. And then we found out that was a solution for having a P here. Sorry, oops. If you recall. Right, so this was our integral number of t's that we ended up with. And so we determined that two translation vectors, could fit in there. And so this already tells you then, if I add these two things to be consistent with a threefold axis there, that T1 has to equal T2 in magnitude. And that comes from what we've done here, because we're taking T and we actually rotate it, right? But given that, the symmetries work, and so T1 equals T2. And of course, the angle between T1 and T2 are 120 degrees. I just wrote this out by hand. You're going to see it show up here. Now remember, this is for n equals 3, but remember before in our formal definition, remember this is 2p, right? That was the same thing as when we had p equals 2 in our other formal definition, right? But remember, with the index notation, n equals 3. And so that's pretty straightforward. We already kind of also talked about that one, but more formally, the magnitudes are the same, and you have 120 degree rotation between them. Let's look at n equals 4. You can probably tell what's coming here. That, again, just to remind you, before, but recall that that was the case for p equals 1. So again, we know what's going on here. I draw t, and then remember I had 90-degree rotation. And of course, if I have two straight lines coming up here, we knew that meant that p equals 1. And I'm able to have 4 fold axes at every translation point, right? And so, in this case, we have the same kind of notation, t1 equals t2, of course, and the angle between them is 90 degrees. And so finally, the case for 6-fold axis, where n equals 3, 60 degrees, will give us the same result, and I'll show you that now. And if you recall, that one meant that I have 60 degrees coming here. Remember, that solution was p equals 0, so p equals 0 was the same thing as n equals 3. And of course, if I look at the symmetry of this compared to that other one, then the very next one in both of these directions produces the same pattern. Remember how we had 2p, which was, two translation vectors from we did 120 degrees. You get the same pattern. So you get the same 2D net as a 3D, so that there's no unique solution there. So when we add those two-fold axes, when we add the different fold axes into 2, 3, 4, and 6, you actually only get 3 unique combinations. And just to summarize, we have the oblique net. The two-fold axis didn't do anything, if you recall, to this. And then, and this, remember, is the only one where in our little solution, t1 doesn't have to equal t2. There's no symmetry, but we can incorporate two-fold axes, but it's not unique. It doesn't do anything, right? So, I could draw two-fold axes here if I wanted to. The hexagonal net came from, so let's make this clear, by the way. The hexagonal lattice was a result of both doesn't matter, just like this one, I get the same thing here. And in that case, we saw t1 equals t2. And of course, the angle between them was 60 degrees, also 120 if you choose the standard cell. Finally, the square net, which is probably, I didn't draw this, but at the end of the day, it is a hexagon where these are equilateral triangles in here. Oops, I should have drawn that further in. All these are, look at here, they're equilateral triangles. Square net, of course, we ended up with p equals 1, and this is n equals 4 for the full-fold axis. And in this case, they're the same size, and the angle between them is 90 degrees. And that's all we're going to have if we only do rotation with translation. So now we haven't used our other operator yet. So now, in the next lecture, we're going to think about what happens if I add a mirror plane to these things. We'll stop here.